Hi, good morning to all. Today we discuss about cascade structure. As the name indicating, here we cascade the FIR filter structures. We can check with a problem. Let's consider this one. Here we want to cascade the following function. The h of z is given as the product of two terms. When we check each term, this is the first term and this one is the second term. When we check each term, it is clear that each term represents a transfer function of an FIR filter. Why? How can we say that? The reason is that when we check the powers, when we take the first term, the powers will be negative. Okay, the powers of z will be negative and it have numerator term only. So this each term, your first term and second term. Okay, each term represent the transfer function of an FIR system. So we can represent this first term as h1 of z and second term as h2 of z. So h of z is the product of h1 of z and h2 of z. So we can realize it as first we pass the signal x of n through the first filter transfer function h1 of z and the output is connected to the second filter. Its transfer function is h2 of z. The combined transfer function is h of z. That is our question. Okay, so here we cascade h1 of z and h2 of z. So we can check its realization. Okay, h1 of z, the expression is given as 1 plus 2z raised to minus 1 minus z raised to minus 2. So it can be realized using direct form method. Okay, that is realized here. So from this realization, we can say that this is 1 plus here z raised to minus 1. This point is z raised to minus 1 and coefficient is 2. So 2 into z raised to minus 1 and minus 1 into, and at this point this is z raised to minus 1 and at this point this is z raised to minus 2. So minus 1 into z raised to minus 2. Okay, this equation is realized here. Okay, that is h1 of z. You can check it. That is h1 of z. That is h1 of z. Then next one here we realize h2 of z. You can check the expression here 1. Then at this point this is z raised to minus 1. So z raised to minus 1 and the coefficient is 1. So 1 into z raised to minus 1. Then here coefficient is minus 1 into, and this point is here z raised to minus 1 z raised to minus 1. So total z raised to minus 2. So this is the realization of h2 of z. h2 of z. 1 plus z raised to minus 1 minus z raised to minus 2. Okay, you can check that one whether it's right or wrong. Okay, h2 of z is 1 plus z raised to minus 1 minus z raised to minus 2. Okay, so that is realized here. So we cascade h1 of z and h2 of z. The output of h1 of z is connected as the input to h2 of z. Then we can check the another problem. Here we cascade the realization. We want to realize this system h of z, that is given as a single polynomial, and here we want to perform the cascade realization. So we want to find its factors. Then only we go for the realization. So from the polynomial, it is clear that the polynomial have 4 terms. So the length of the filter is 4 and the order is given by the length minus 1. So order is 3. So we have 3 factors. How can you compute its factors? First of all, we want to convert the powers as positive. Okay, here the polynomial powers are negative. We want to convert it into positive powers. How can we do that? We multiply and divide it by z cube. Okay, so multiply and divided by z cube. So this term become this one. This expression become like this one. We multiply and divided by z cube. So there is no change in the expression. We multiply and divide. Okay, so we get the expression like this one. Okay, then next we move on to find the factors. Okay, we want to find the factors. How can we do that? Using trial and error method. Okay, substitute z is equal to 0 or plus or minus 1 or plus or minus 2 or plus or minus 3 like that. Okay, at a particular point you will get the value of expression becomes 0. In that manner you can find the factors. Okay, so when substitute z is equal to minus 2, this polynomial becomes 0. So we can say that z is equal to minus 2 is a factor. That is one factor. Okay, so we can say that z plus 2 is the factor of h of z. Okay, one of the factor is computed. So how can you compute the remaining factor? Using, we can compute it. How can we do that? First of all, we find one factor, that is minus 2. Then we represent the polynomial coefficient. That is here z cube plus pi by 2 z square plus 2z plus 2. And we write the coefficients here. Then what is the next step? The first coefficient is taken outside, that is 1. Next we multiply 1 with this minus 2. You will get minus 2. Then we go for the addition. 5 by 2 plus minus 2 is 1 by 2. Then we multiply 1 by 2 with minus 2. You will get minus 1. Then add 2 plus minus 1 is 1. Then 1 into minus 2 become minus 2. So when we add it, it becomes 0. So these represent the coefficient of the remaining polynomial. So that is, here the powers are z square plus 1 by 2 z plus 1. I think you already studied this method. Okay, if you get a factor, how can you compute the remaining polynomial? Okay, so we can represent h of z as this product of these two terms, that is z plus 2 and z square plus 1 by 2 z plus 1. Okay, the numerator can be represented like this. Okay, next step is, what is the next step? Next step, we want to realize the system. Before that, we want to check that each term is the transfer function of an FIR system. For an FIR system, the powers of z must be negative. So we want to change the powers to negative. For that, we take z from the first term and the z square from the second term. Then we divide with the denominator. So you will get the two terms like this. The first term is 1 plus 2 into z raised to minus 1, and second term is this one. When we check each term, it is in the form of the transfer function of a FIR system. So we can consider it as h1 of z, and these are h2 of z. Then we can go for the realization. We realize h1 of z, then we realize h2 of z. During the realization, when we go for the realization of h2 of z, okay, you can check the coefficient. What is the significance of these coefficients? Here, when we check this coefficient, it is clear that the coefficients are symmetric. Here the coefficients are symmetric or have the common coefficient. So we can realize using linear phase realization method. Using linear phase realization method. So h2 of z is realized using linear phase realization, and h1 of z is the direct. Okay, you can check it. This is the h1 of z. We use the direct form method. In order to reduce the number of multipliers, we go for the linear phase realization. h2 of z is realized as a linear phase filter. Okay, and cascade h1 of z and h2 of z. You will get the net resultant function. Okay, that's all. Okay, thank you.